好的，那我们现在进入到下一个环节的部分。哦，对，这个联络方式差点给忘了这个是因为刚才那个 OMIDI 的那个联系方式里面那个视频里面没有放，所以我在这边单独给放了一下出来。所以有需要的小伙伴可以截图一下，然后后面就跟 Philip 的话做一些联系，看有没有一些可以合作的地方。OK，then let's come to the next part. Okay, Justin, are you online?
Yes, I'm online.
Hi, nice to see you. I know it's too early in United States. You are now in Seattle, so let's make things quickly to tend to your part. OK，我们非常欢迎 Justin 这次来参加我们的这一次的一个演讲，因为他现在在美国，在西雅图，所以现在可能是半夜3、4点的时间，他来参加我们这一个会议，所以是非常感谢。OK，now let me do a short questions about yourself. And Justin 的话，他是来自于这个美国华盛顿大学的一个博士生。那么呢 ，Justin 他关注于在用计算解决的方法去降低高质量的一个医疗服务的成本。Justin 所在的团队研发了3款低成本基于手机的检测设备，用于检测新生儿的中耳疾病。相关的文章发表在了多种跨学科的期刊，例如 Nature 以及这个 Nature Communication。那么他演讲内容的话，就是他们的团队利用智能手机搭载一个改装过的耳机线，实现了耳声发射仪的基本功能，在114名患者身上进行测试，与商用设备的结果非常的吻合。其团队同时还研发了简易的中耳分析仪和耳窥工具。讲者将介绍这3款产品的设计思路，并且就临床数据进行一些分享。那么接下来我们会把时间交给甜甜，那么还是请大家记得一定要扫码填写问卷。OK， 好的，谢谢。我们把时间交给甜甜。Justin, they will first play your videos. After the video is the Q&A time, so you can be online to answer the questions from the audience. OK， 甜甜把时间交给你。
Hi, everyone. I'm Justin Chan, and I'm a PhD student in the Computer Science and Engineering School at the University of Washington. The focus of my research is to develop new hardware and software systems that can significantly increase access to medical devices and diagnostics. Specifically, my approach to selecting research projects is focused around the central issue of whether medical devices can be manufactured for orders of magnitude less than conventional devices without sacrificing any clinical accuracy. Today, I'll be presenting my research on a frugal and accessible audiology toolkit, and the toolkit consists of 3 devices. The first is a tool that's designed to screen for newborn hearing loss using earphones. The second is a smartphone-based tool to detect ear infections. And the third is a low-cost tympanometer that can detect a wide range of middle ear disorders. It's pretty common practice, especially in high-income countries, to adopt guidelines for universal infant hearing screening using autoacoustic emissions or auditory brainstem response testing. In spite of this, the test equipment remains pretty expensive, and it costs upwards of $6,000 even. And this contributes to a very limited amount of hearing screening in the low and middle income countries. In some of these countries, such as Kenya, getting access to the hearing equipment often requires pretty long travel times to an urban setting and even longer wait times, having to wait hours just to meet with a specialist. So let's get into the details of this test, this autoacoustic emission test. Although conventional devices are pretty expensive, the principle of operation here really only requires a pretty simple setup. It only requires 2 speakers to send a sound stimulus into the ear and a single microphone right by the ear tip to record the stimulus. And we designed a low-cost probe using off-the-shelf components. It costs just about $10, and you can see the price breakdown here. There are those 2 earphones that really only cost $5, the microphone which costs $2 by the ear tip, and some remaining components, some silicone tubes and some adapters and connectors that cost only about $2 in total. The smartphone itself, you can buy a budget smartphone these days for only about $40, which is pretty cheap, making the total cost of this device only about $50, which is a pretty large decrease compared to some of these conventional devices, which can cost upwards of $6,000, which is over 100 times more expensive. Now, in order to actually elicit OAEs with our test, we just have to send two tones through these two earphones, this F1 and F2, F1 through the left earphone and F2 through the right earphone. The tones travel along these silicon tubes out through the ear tip, and it travels right into the cochlea, which generates an OAE at another frequency, 2F1 minus F2. And then the microphone can actually listen to these OAEs and try to detect them. You can actually test at multiple frequencies here. So you can select F1 and F2 around, say, 1 kilohertz to test hearing at that range. And you can set F1 and F2 to like 5 kilohertz if you wanted to test hearing at a slightly higher frequency. Now this plot here actually shows what we're sending into the ear. The two red tones here are the F1 and the F2 stimulus tones. And the OAE level is the green tone that is sent back out of the ear at 2F1 minus F2. What's really interesting is that OAEs are often very soft, and they're often even below the human threshold for hearing, which is 0 dB SPL. And you can see that because of that, humans often can't even hear them. And in order to actually tease out these very, very soft sounds, you need some signal processing algorithms to run on the smartphone to detect these very soft sounds. We ran a clinical study to test our device at Seattle Children's Hospital. In fact, we did this across 3 different clinical sites and recruited 201 patient ears from 1 week and 20 years of age. The really nice thing here is that we didn't only have specialists test out this device. In fact, during our study, we had our system performed by undergraduates, research coordinators, graduate students like myself even, and all it requires was just some very basic training to be able to use this device. It's not something that must be performed in the hands of a specialist. Now, the goal of our study was to see if our smartphone earphone OAE system could be used to screen for hearing loss. So to get the ground truth or the reference of whether a patient actually had hearing loss, we used a combination of clinical and exam review. And this included patient audiogram information, acoustic brainstem response testing, and so on. And the clinician at the end made the call for whether you could classify the child as having hearing loss or not. So of the entire cohort, so of this entire age range, our sensitivity was 100% and our specificity is 89%. What this means is that for all the patients that actually presented with hearing loss, we were able to detect that 100% of the time. We did not miss any of the patients that presented with hearing loss. So this is a really nice result from our study here. This is showing that whenever the patient has hearing loss, it's very, very likely that our device can actually flag that and potentially refer the patient for further screening or further diagnosis. Our study in this was actually recently published in Nature Biomedical Engineering, which I'm really excited about. I want to point to a really key subgroup here. Within this population, the subgroup that we really care about is the 0 to 6 month population, because that right there is the infant population. And OAEs really have the most amount of benefit to this group because, as I mentioned before, this is the group that's unable to physically respond to conventional audiometry tests. Now, ideally, OAEs are often performed while these patients are asleep so that they're not moving about. They're pretty still if they're asleep. But in reality, when we were performing these tests, they were often moving around sometimes. So the cool thing here is that we were able to implement some nice noise detection algorithms that was able to just look at the parts of the signal when the patient wasn't moving around to get those OAEs. And if the patient was moving around the entire measurement or way too much, we would just alert the user to say that the measurement needs to be reperformed. So we were able to collect 74 measurements of infants. 74 infants participated in the study. 74 patient ears participated in the study. And we can see the accuracy of our earphone-based device in blue here and the commercial device in orange here. And you can see that for different age ranges from 0 to up to 6 months, both these devices had pretty comparable accuracy, which is really nice, and we were able to detect children that had hearing loss 100% of the time. So just this summer, we had an opportunity to visit our clinical collaborators and government officials from the Ministry of Health in Nairobi, Kenya, to discuss opportunities about how we can potentially deploy these devices in their clinics in the near future. Now, if we take a step back and look at the bigger picture here, where does our device stand in? Our device really helps with early detection at the newborn stage, which I think can really help with some of the screening in Kenya, because especially in the capital of Kenya, in Nairobi, there are 40 out of 47 counties there that do not have any hearing professional center. So we started an international group called TUNE. You can see the URL and the logo here, towards universal newborn and early childhood screening in Kenya. And this is an international group comprised of clinicians and government officials, and we're planning to run our clinical test in the very near future. I would now like to transition to the next project, which deals with probably one of the most common ear problems, which is ear infections. Now, in this project, we devised a frugal approach to detect middle ear fluid, which is really the cause of ear infections a lot of the time, using just a paper cone and a smartphone. For these reasons, the American Academy of Otolaryngology has called for research into a brief, reliable, and objective method to detect middle ear fluid. In this talk, we present the first smartphone-based tool for detecting middle ear fluid just using sensors on a smartphone, and this work was published in 2019 in Science Translational Medicine. We ran a clinical study on 98 patient ears and showed that our tool was able to achieve specialist-level accuracies. And we showed that parents were able to run our app as accurately as trained clinicians. So how does this technology actually work? At a high level, our tool is designed to send soft acoustic chirps into the ear canal and probe whether there's fluid behind the ear. And the chirps are sent through this paper funnel. Now, the funnel actually focuses the sound in and out of the ear, and it prevents the sound from dispersing into the air. So it goes into the ear canal, impacts the eardrum, and some sound, and the remaining sound is reflected back out of the ear canal. In an ear that does not have fluid, the eardrum will actually absorb most of the sound frequencies. Because the eardrum, it's pretty thin. It's only about 0.1 millimeters thick. So it's about as thin as a piece of paper. That's pretty thin. So most of the sound is just going to go through. Very little will be reflected back. Now, how do we actually determine this? What we do is we listen using the microphone on the smartphone to record the sound that's reflected back. And you can plot the frequency profile, which you can see here in blue. Now, in a normal ear, the frequency profile is pretty broad and shallow in the frequency domain. And you can interpret this to mean that most of the sound is just going through. But in an ear that does have fluid, so you can see that yellow block behind the eardrum, that's the middle ear fluid, the fluid will actually restrict the vibrational capacity of the eardrum. So the eardrum is going to be much, much more stiff. And when you send sound towards the eardrum, most of it will actually be reflected back, because it's kind of like sending sound towards a solid object like a brick wall. Most of the sound will be reflected back. Now, the reflections will interfere destructively with the sound that's still going into the ear canal. And it creates a frequency profile like this due to the destructive interference of the reflections and the incident sound waves. It's a much deeper. Natural question you may then ask is, how do you get the ground truth to really know if there's fluid? How do you actually get a reference point to compare the performance of our device? Because as you know, it's unreliable to see behind the eardrum. So how do we actually perform this reference test? This is done through a process known as myrigotomy, which means that an incision is made into the eardrum to actually see this fluid. So you can see here this little video where an incision is being made into the eardrum. Now, this is actually a pretty routine procedure, and it's done for children that are getting ear tubes. So it's a very common procedure. We evaluated our tool in a cohort of 98 patient ears and ran our smartphone-based test in the preoperative area with parents and children just before the children were scheduled to get ear tubes. Our patients were between 18 months and 17 years of age, and we ran our test on an iPhone 5S. We obtained an overall sensitivity of 85% and a specificity of 82%. This is actually comparable to these specialist tools like pneumatic otoscopy and tympanometry, which is really nice. So you may ask, does this require a special smartphone to work? The answer is actually no. Our system leverages the fact that a majority of modern smartphones these days have the speaker and the microphone positioned at the base of the phone, as you can see in this figure here. And you can envelop the base of this phone with a paper cone. And this geometric configuration is actually the same for all iPhones ever since the very first iPhone. This configuration also remains the same for other lines of smartphones like the Samsung Galaxy and the Pixel. And it's unlikely that this configuration will change simply because this actually helps with noise cancellation during phone calls. So there's actually a functional reason for why the speaker and the microphone are placed in this particular geometry. And we can actually exploit that, of course, for a purpose that it was not intended to, which is to use it to detect middle ear fluid. The next question you might ask is, suppose you want to do this test on a new phone, like the new iPhone 14, can you just use the machine learning model built on data from the iPhone 5S that we collected all our data on? The answer is, in fact, yes. We were able to train our algorithm on curves from the iPhone 5S and apply a normalization procedure that can adapt the model to other phones. We then test this adapted model on ears collected on other phones like the iPhone 6S, the Galaxy S7, and the Google Pixel, and obtained accuracies from 80 to 92%. And this is really nice because it means whenever you want to support a new phone model, you do not have to run an entirely new clinical study to collect the data. We also tested how easy it was for parents to assemble the paper cone. So we gave them instructions to cut, fold, and tape the cone, and they were all able to do this within about 3 minutes without any prior exposure to the project. Now let me show you a quick demo of how you could use this tool to perform testing on your own child. To ensure that we can bring this technology to the homes of millions of people, we started a company, Wavely Diagnostics, which is in the process of commercializing this technology. Now, I'm going to be transitioning on to the third and final project of this talk. As we were working on the urine infection project, a lot of people had asked us if we could detect a variety of other middle ear conditions, because ear infections is just one type of ear condition. There are a lot of other things, like eustachian tube dysfunction that can be caused by negative middle ear pressure, or otosclerosis, which is caused by an overly stiff eardrum. Now, there's a test to actually detect all these things, and it's called tympanometry. So tympanometry is a key test to measure middle ear function because it provides an objective and quantitative test of eardrum mobility that is often used to make these diagnoses. And of course, accurate screening for these middle ear disorders can mean more timely referrals to medical interventions, and it can reduce the likelihood of a very serious complication from developing. So what we developed was an inexpensive smartphone-based tympanometry system that can be used as a portable smartphone attachment. And it only costs around $30 and can fit in the palm of your hand. So let me show you a demo of how this works here. In this work, we introduce an open source smartphone-based tympanometer to measure middle ear function. Our smartphone attachment consists of a syringe to carefully change ear pressure and move the eardrum. During this pressure sweep, an acoustic tone is sent to the ear. The recorded sound is converted into a chart known as a tympanogram, which can be used to quantify eardrum mobility. Okay, so let's take a look at what's at the heart of this device. Right in the inside is a pressure transducer, and that's used to actually change the amount of pressure within the ear canal. So it pushes the eardrum forward and it moves it backwards as it introduces more and takes away a little bit of pressure to the eardrum. So a commercial tympanometer typically uses a pretty expensive setup for this, but we asked what's the cheapest pressure transducer that you can go to. And as it turns out, we designed just a very cheap transducer just using a cheap syringe that just costs less than $1 to change the pressure within the ear. Now the syringe is attached, as you can see here, to a stepper motor to move the plunger backwards and forwards very, very carefully at a sub-millimeter precision. And you can perform this pressure sweep very precisely. The motor is then connected through a series of pipes to an ear tip that just goes into the ear, similar to kind of like a headphone. And our system is designed with safety in mind. So we have a pressure sensor to make sure that the pressure in the ear only remains between these very specific pressure bands. Now, during the pressure sweep, the attachment also sends an acoustic tone into the ear canal, sends it out through a speaker, and it records what's reflected back using a microphone. And based on how much sound is actually reflected from the eardrum as the pressure changes, you can actually convert that information into a chart known as a tympanogram that quantifies the mobility of the eardrum. Now, to evaluate our device, we conducted a study on 50 pediatric ears and did this test in parallel with a commercial tympanometer. And we targeted patients with a variety of middle ear disorders, including patients with ear tubes, eardrum perforations, otosclerosis, and even negative middle ear pressure. We compared the systems on key metrics here. So we compared the height of the tympanogram with the peak admittance, the peak pressure, so at what pressure the peak of the tympanogram was, and also the ear canal volume that was measured using the device. So these are the three metrics here, and these graphs are intended to show on the x-axis what was measured by the commercial device for these three metrics, and on the y-axis we can see what the smartphone measured for all these three metrics. And the takeaway here is really that we were able to get a good correlation on all these quantitative metrics and have comparable accuracy to the commercial device. We also had a panel of pediatric audiologists review the tympanograms, visually review them based on what was measured on the smartphone and what was measured on the commercial device, and to classify them into 5 clinically relevant classes. So based on this classification scheme, they had an agreement of 86%, which is a good agreement between both devices. So in summary, today I presented 3 different projects. The first is a low-cost probe design to measure autoacoustic emissions that can potentially be used for universal newborn hearing screening programs in low to middle income countries. The second is a smartphone-based tool to detect ear infections using just a paper cone. And finally, I present a smartphone-based tympanometer to provide an objective quantitative measurement of our eardrum mobility. All of these products are done at a much lower cost than their conventional commercial counterparts and still have comparable accuracies. Now, the thing that all of these products have in common is that they can significantly decrease cost of access to medical devices and make it easier to access healthcare. They all leverage the fact that smartphones are ubiquitous around the world and can be used to perform many of the functions of these medical devices. And with these low-cost medical devices, we could potentially make it easier to detect medical issues early and refer patients to get the necessary care that they need. You can find more details about all these products at the TUNE website at the link below. Thank you very much.
Okay. Hi, Justin. Nice to see you online.
Hi.
Okay.
Yeah, I see one question already in the chat.
Yeah.
I can just answer that.
Okay. I write down 4 questions. So, Song, are you there?
Oh. Yeah. So, hi, Justin. How are you? Can you hear my voice?
Yeah, hi. Oh, okay.
Yeah, hi. Yeah, Styla have already collected some questions from our audience. So let me ask you some questions.
Okay.
The first one is about collaboration for the auto acoustic emission. How to collaborate the two tubes?
Right. So, as I'm sure a lot of you know, because you're all familiar with audiology, for OAEs, when you're sending those two tones, they need to be calibrated to a specific sound level. So typically, the first tone, F1, is calibrated to 65 dB SPL, and F2, the second tone, is calibrated to 55 dB SPL. So for that, we actually just use just a regular sound level meter, and we have to do some manual calibration. So even if the length of the tube, you fix the length of the silicon tubes to a fixed length, you still need to double check this calibration process. You might ask, okay, how often do you need to calibrate it? For our study, we calibrated it once and it worked for about 3 months. We didn't have to keep calibrating it. But how do you know if there are issues with the calibration? Typically, in a real commercial device, you would take a measurement in open air, just no ear, just in open air. And there should be 0 OAEs. And you should also put it in a tube, and there should also be 0 OAEs. So if you perform those tests and they do not work well, then you have to recalibrate the volume, the sound level volume. But we think maybe this is something you have to do maybe every 6 months or every 12 months. So it's not a frequent process. Does that answer the question?
Yeah. So I'm going to translate it.
Okay. Yes.
Yeah. So 刚才 Justin 说了，他说就类似于，因为我们都是比较熟悉听力学的，或从业者，就是会跟我们传统的 OAE 是一样的测试和校准的方法。然后因为我们的声音都是，因为有 OAE 会测2个声音嘛 ，F1 跟 F2，然后我们会在设定里面会有65 dB 的这个声音啊。然后他刚才也说了，说我们就像正常的，我们当然需要去做校准啊，大概是3个月的时间，然后我们先把这个 tube， 然后放在一个干净的空气当中，然后去看它是不是0 dB 的这么一个声音，然后再放在 tube 里面，如果也是0 dB 的话，然后那就是对的。如果发现有些问题的话，我们需要去做重复的校准，然后当然如果在正式的商业化之后，我们需要在定期的在6个月或者12个月，然后做同样的校准的这个动作。好，大家有什么问题吗？
刚刚那个对，第一个问题就是季飞老师问的啊，他其实问的是 two tones，不是 two tubes， 是我写错了啊，我不知道有什么区别，因为那个因为宋你自己是专业的听力学毕业，你看我不知道这个 tube 跟 tone 的话，这个对回答会有些影响跟变化吗？它 two tone 应该是指的是 F1 跟 F2，你看一下。
会有一些影响 I think so. The tones about the FE,
yeah,
the frequency
it's
one,
the tones,
yeah, the tubes.
Yeah.
Okay. I understand the difference. So, hi Justin, could you please explain the question 1 again, because the tubes and tones quite.
I think the person is asking about the sound levels. How do you make sure it's the same sound level? So I think whatever I said is correct. So I think whatever you translated is also correct.
Okay. Yeah.
Yeah.
Okay, Stella, so 他应该是问题不大，就是类似于刚才小新也已经说了，就是他确实是按照 tones 去解释的啊，因为他说就是我们的 tones 就是规定好的，因为它是应该是 DPOAE 吧，需要有2个差半个波频的这个频率进行一个刺激啊，所以他觉得如果说是我们只要设置好的话，播放声音的就是可以的。
OK， 好了，我刚刚也想问一下那个宋同学哈，就是因为您是因为专业的听力学的这边嘛，那就是因为你看他其实介绍了一下这个 OAE 啊，包括这个综合分析仪嘛，那从你专业的角度来说， 就是说如果去操作现在传统这些专业的设备的话，其实会不会对于就是说这个操作者其实还是有蛮高的一些标准的要求，包括环境啊这些会不会有一些比较大的要求？因为我们想知道说他做这个简易版是不是确实说是有很大的一个优劣性的一个地方？这个问题可能想你先回答一下，可能让我们的观众更了解一些。
我首先觉得就是首先 OAE 的原理并不难所以它只要保证了话，其实从业者的准确性，就类似于我们塞耳机进到耳朵里的时候，它会不会有这个缝隙啊？会不会 leaking out？就会不会有没有塞紧的情况？其实是会对测试本身会有比较大的一个影响，因为它在它的 study 里写了它的准确性和一致性还是比较高的，然后也发过 Nature 上。我对于它的这个学术上的这个疑问不是很大，我更关心的是，比如说真正的用的人，他会不会能真正的正确的使用它的设备。
谢谢你的回答，可以继续第二个问题啊。Thank you.
Okay, Justin. So next question. You have mentioned 3 apps. Can we download in China now?
Okay, so the OAE one and the tympanometry one, we've released the source code for that. The source code the source code has been released for that. So you can go to my website. I put my website in the chat, and then there should be links to the code for both of those projects. In the publications there should be links to the GitHub code for the OEE project and the tympanometry project. For the middle ear fluid project, we're currently commercializing it within the US. So the intent is that would be currently the plans are for commercialization within the US, but the other 2 are open source, so anyone can access that.
Okay, thank you. So, Justin 的应用应该是有一个网址，然后咱们可以点进去，就会直接链接到 OAE 的应用上。然后对于第二个middle ear 就是中耳的检测的话，应该已经是在美国已经正式的商业化了所以我们任何人都可以去登录上去。如果Hi Justin.
Sorry. I think for the middle ear fluid one, that is not public. We're still working on that. That one is not public yet. But yeah, just want to clarify.
Justin 应该补充，对于那个探测有没有中耳炎的那个应用，目前还没有公开。Okay, so another question from our audience. Is there any requirement on the thickness of the paper?
No. We tried different paper thicknesses. We tried very thick paper. Actually, very thick paper worked better. We just use regular paper, just any just some paper on my desk. We just use this type of paper. This will also work. It doesn't have to be a special type of paper for it to work. So you can actually try it yourself. In the publication, there's a template, and you can actually cut out the template, print out the template, cut it out yourself, and you can put it on your phone actually, and you can try running some experiments on your own if you want.
Okay. 所以刚才贾青说，其实他对于这个测试对于纸张没有什么要求，就是正常的非常普通的纸就可以，但是他觉得可能thick 就是厚一点的纸会更好一些但是我们需要把它裁剪成相对应的这个形状，然后保证形状正确的，然后套在手机上才可以进行测试。So another question, these works were actually based on the DP OAE. How about the SF OAE? Can we do
that's a very good question. We haven't tested SF OAEs because the main focus of this is for newborn screening. So that's actually why we selected DP OAEs. We're actually also working on something for TE OAEs now. We're currently working on that. But the SF OAE thing, that's actually very interesting. I think in theory, you might be able to get that to work with our device, but we just haven't tested it yet.
OK, thank you.刚才贾晶说，因为我们目前针对的主要是新生儿的筛查，所以目前 DPOAE 是最适合的一项测试。我们目前还在探索，比如像 GE-OAE 或 SF-OAE。他觉得话，我们会在未来研究里会去做更多的 OAE 的测试啊。OK.
Yeah, the first one is the new one.
The new one.
Yeah, and the third one is the new.
So the temple of the paper put in the ear, is there any chance of leaking out? And do I have any requirement about the environment, like in the quiet environment, or is that still okay in the noise environment?
That's a great question. For the ear test, you do not need a seal. You can just place it just right outside the ear. So it's just a very, you do not need a tight seal. This will work with some level of background noise, but obviously if the patient is crying and making a lot of noise, it's not going to work. So it's the same as most other audiology tests. It needs to be a somewhat quiet environment, but it doesn't have to be extremely quiet. In a normal home, it's okay.
OK, so 刚才贾斯汀说他是个非常好的问题，他不用担心在耳朵会有泄漏，他只要在耳朵旁边就可以，并不一定需要它是密封的啊。当然对测试环境来说，当然如果孩子正在哭泣，然后造成很大的噪声，当然是没法进行这项测试的。但是我们也不用 extremely， 就是不用非常非常的安静，它只需要说在正常的环境当中或者在家里都可以进行这项测试啊。So the last question, I think, do you have already got a patent?
Oh, sorry, can you repeat that?
Oh, sorry. Do you have already got a patent?
Oh, so the tympanometry and the OAE one are open source, and because it's open source, we're not patenting it. The middle ear fluid one, we do have a patent on it, so the patent has been filed and that's public, because we're trying to, that's a commercial business, so we're trying to actually make that as a product to sell, but that one has a patent.
OK, thank you. 所以对于 OAE 来说，它是其实一个开放性资源，是免费提供用户去使用的。那对于像中耳测试相关的产品，它是正在进行一个商业化的情况啊，希望它通过它来盈利。OK, do I have any questions? So 还有问题吗？
屏幕中第一个是回答了没有？我好像稍微有点漏掉了。就是这个 calibration 是不是需要到专业的机构去做 ？Has you answered this question?
Oh, OK.
Forget this one. Yeah. This is from Dr. Ji.
Do we need to do the collaboration in the professional organizations?
No. The tympanometer and the OAE test, you can just have a technician probably calibrate it. So most of the time it was me calibrating it, but I asked some of my colleagues to calibrate it as well. I just gave them some instructions, taught them for 5 minutes, and then they were able to calibrate it. So it's not a very difficult process.
OK, thank you. Justin 刚才说他其实并不需要到专业的机构检测啊，它并不是一个非常难的技术。OK, Stella, do you have any questions?
No, I think it's all for the question. And thank you, Salt. You have do a great job.
Yeah. Thank you, Justin.
Yeah. 对，宋，我刚好也想问一下你一个问题哈，就是关于他那个中耳炎的这个就是流脓的这个处理的话，因为他用的是一个指锥嘛，那我不太清楚现在我们在国内一般传统的做法是什么，有比它更先进吗？因为我看他用的是一个声波的那个发射的那个来探，但是好像我们国内现在一般是用那个耳内镜的这种方式在检查，是吗？
对，其实在国内的话，我们其实是很多种检查相结合的。就比如说，我们先会用耳内镜看，如果很严重的中耳炎或在急性期的时候，那其实我们很容易就看到它有中耳炎的一个情况，比如它的鼓膜已经有腐烂，或者明显的看见很多气泡在鼓膜后面，或者有一些发红啊，那这些都可以判定为是中耳炎，可能都不需要经过其他的检测。但是，一般的大的三甲医院，我们可能还会做一些，比如像 tympanometry，就是鼓视图啊，我们看一下它的这个反射是不是一点也没有了啊。这样我们2个判断加一块就可以判定它可能是有中耳炎，然后根据病史的询问，那基本上就可以有95%的一个相当于一个 golden 的 rules 就可以判断它是不是有中耳炎了。
OK，thank you，thank you，谢谢你的回答。因为这个让我想起来，英国有个发明，包括澳大利亚的 Nail，他们上次也发明了一个Nail 的，上次那个 Jessie 的分享也提到了一点，说他们是可以应用 AI 的一个大数据，就是他们给这个机器喂了好多一些那个耳道畸形的一些数据，然后所以变得他们如果在用一个基于手机的一个耳窥镜的时候去探这个耳类的时候，就是它可以系统可以识别出来说它大概是哪一种中耳疾病，所以我觉得这个还类似于像这个的一个升级版，我这个只是补充说明一下。OK，刚才
Okay, I think I forgot one question. Sorry, Justin.
OK，
I think it's the last question. So the codes are open source,
yeah.
but how can people get those little handwords and get them assembled?
Yeah. So for the OAE one, the hardware, if you look in the paper, the supplementary information in the paper, we list all the hardware components so you can replicate the hardware. For the tympanometry project, we've also listed all the hardware components and the supplementary information. And the PCB files are also online. So if you look in the publication, there are links to how you can actually get access to the hardware things. Yeah.